Hi, everybody. My name is Hadar Weiss. I'm one of the founders of Peer5. First of all, I wanted to say I'm really excited to be here. It's great to meet old friends from 2012, from the happy days of WebRTC, and just very nice to see how this community grew and became what it is today. So super exciting to be here. So Peer5 is a peer-to-peer CDN. We are one of the companies here that use the data channels API, not the main WebRTC API. We started in 2012, and it was the first peer-to-peer CDN that was based on WebRTC. And today we have scaled, and we became the largest commercial peer-to-peer network. In some metrics, we are the largest CDN in the world, and all of it without buying any servers. I want to explain a bit how we scaled and what are the different challenges we had to solve in that journey. Let's step back for a second. I hope everybody knows what's a CDN, but just in case, a CDN is a content delivery network. It's essentially a distributed network of servers. It serves usually thousands of servers that are installed around the world. And when you hit a website, you would get the content from a nearby location and not from the origin server that is somewhere in a data center of AWS or whatever it is. You may even get the content from an ISP next door. So this was essential piece for building the internet. This is how we load web pages. This is how we load apps that you build for WebRTC. And it was also applied for video. So all video streaming services that you use today are using CDNs, thousands of servers as cache that caches the video chunks. We believe in Peer5 that we need further decentralization. The internet was supposed to be completely decentralized, but in the end, what we're using is servers. Anything we want to do online is with servers. And it has some bottlenecks, it has some issues. And we want to decentralize it all the way to the edge, all the way to the end users that will cache the content, and we can actually consume the content from that edge. The reason is that server capacity is limited, and we feel it today mostly in video streaming. So I don't know if anyone here tried to watch the McGregor-Mayweather fight. Didn't really work that well because there's a spike, and whenever there's a spike, you would see buffering, you'd see issues. The reason for this is just because each CDN has fixed number of servers. You cannot magically deploy more servers. Usually it's around, the top CDNs around the world have capped at around 100 terabit per second. When you think about the World Cup in football/soccer, whatever you want to call it, next year, more than 1 billion people are going to watch that game. Mostly of them are going to be on television, unfortunately, but everybody wants to watch it online. And when they do, it can generate 15,000 terabit per second at spike. So we're orders of magnitude far from serving the amount of users we want, and that's Peer5's mission to be able to take as much bandwidth as possible to our network and relieve the server infrastructure. And peer-to-peer and WebRTC just works perfectly for this, because the more viewers that will watch that football game, the better it's going to work. They're going to serve other users their content. We're going to help each other because we watch the same game, watch the same content, and we buffer anyway those video chunks. So we can just share the content. That's exactly what we do. But I want to emphasize one point here. It's a peer-assisted model. It's not that we're saying stop using servers, servers are bad. Servers are great. This is what we use for the seed or the origin of the network. So imagine you're the first viewer of that football game. Obviously, you'd need to stream that content from somewhere. So you're going to get that content from the edge, from the CDN like you do today. It would be using HTTP, and that's just fine. We're talking about 1 million concurrent viewers that are watching the game. Most of the communication, most of the bits are going to be delivered within themselves with something called mesh network, which basically is unstructured network of users. And our goal as Peer5 is to connect the best viewers. So you start watching that game. Immediately, we want to connect you with the best viewers that are good for you. Typically, our magic number is 15 viewers that you're going to connect to. You're going to start fetching different chunks of video from them, synchronize everything, stitch it together, and play it in your video player. Whenever you have to, you still always can fall back to the CDN. So our role, if you think about the scalability, the scale of this, is to take as much as possible to our mesh network, and only when needed, we go to the CDN. But we still preserve the user experience, so you will not have more buffering. It actually works just better. And the results are pretty good. And during some peak hours, we already reached 99% efficiency, meaning 99% of the load of the request were offloaded to the peer-to-peer network. Just 1% of the requests still had to go all the way through the server infrastructure, the CDN. That translates to 100x in scalability. So if today CDNs can do 10 million concurrent viewers at peak, with us they can do 1 billion, because almost nothing would go to that CDN infrastructure. And I want to share a bit information about that. So today, we facilitate 1 billion WebRTC connections. So it's important to emphasize that our use case is different. It's not Google Hangouts. It's not that those connections are explicit. Again, when you start watching a video, we will connect you with the best viewers for you, and we will continuously switch them. Sometimes a user can, throughout a viewing session of a full football game, or let's say Game of Thrones, switch different viewers until they're working with the best viewers for them. And that creates just tremendous amounts of connections that we have to create. So on an average day, we create 1 billion WebRTC connections. In terms of SDP messages, we generate 2 billion a day. And our backend needs to sustain 15 million WebSocket connections. Everything here is without turn. It's just stun. And it's just WebRTC data channels connections, nothing else. During peak hour, we need to get to 2 million. We have reached 2 million concurrent viewers, so 2 million WebSocket connections that the backend had to deal with. And we process 240,000 messages per second, and 145,000 WebRTC connections are created every second during those times. So that creates a lot of challenges and a lot of learnings during those years. And I want to focus on 3 that I think are interesting and very, very related to WebRTC. Again, our use case is a bit different than most WebRTC apps, and we picked just the ones that could be applicable and very, very WebRTC related. So here are the 3. First of all, WebRTC is pretty chatty protocol. It creates a lot of messages. Whenever you want to initiate a session, sometimes more than 10 different SDP and ICE messages can be exchanged until you finally have a working connection. That's very wasteful, in our opinion. It's very chatty. The other thing is just SDP is text-based. It's wasteful. And we wanted to optimize it. And the third point here is that sometimes connections fail. Sometimes bad users create noise in the network. They are not well connected to other users and just create an overall noise in the network. And I'll talk about it in a second. So first topic is how we made WebRTC less chatty. Again, our use case is not one-to-one voice call. Latency is not a huge deal for us. If we introduce another 100 or 300 milliseconds latency between 2 endpoints, that's OK. And what we discovered is actually WebRTC generates, each party in the WebRTC session generates messages. And sometimes it doesn't have to be interactive. A few messages can be queued together and be sent as one piece, and the session can still exist and be completely operable, and there's no problem with this. So we just have some thresholds, if I recall, of 100 milliseconds that we wait for the next SDP or ICE message. And once we feel, OK, that's it, the endpoint, that user does not need more messages, we send it as one bulk message. And this is something you can check for your app if this is applicable. I think for most WebRTC apps, it should be applicable because an extra 100 millisecond latency usually is not a big deal. And it creates huge savings. So 65% reduction in total messages because of this optimization of grouping messages together. The other thing that we did is to compress the SDP messages. It's worth to mention that there is an open source project that does that as well. And hopefully, the browsers themselves in the future can do that better. We implemented our own proprietary dictionary-based compression. It's very easy to implement. If you need help with that, ping me later. It just replaces predefined SDP keywords with characters. And also, it reduced, so the result is about 54% reduction in the sizes of the messages. So the bandwidth you need is much lower. OK, third optimization. We noticed that there is a high correlation. I mean, it's pretty trivial that there's high correlation between the success rate of a connection to the overall efficiency we see. So efficiency, again, is the percentage of traffic that we can offload to the peer-to-peer network from the server CDN. Whenever the connections are very successful, whenever we can facilitate connections that work, that's great. That means that more content can be sent on that mesh network and less needed to be used by the CDN. So we really wanted to optimize the success ratios. I'll give another example where it matters the most. Imagine just 10 viewers are watching this huge, a small soccer game. If we have 10% more failures on the connections, it's a huge impact. It means that some users may not be connected to any users, although they could have, and will consume the content, will fall back immediately to the CDN. So it's a very important metric to optimize. And apparently, whenever you're failed on your first attempt to connect two end users somewhere around the world, it doesn't mean that they could not connect again. They cannot attempt another connection. And again, we're talking about only stun. So we see about 62% success rates on the first attempt. Then we try again, we see 18%. So definitely worth trying out another attempt for connection. There's diminishing returns on this, obviously. If you do it 100 times, you will not see significant benefit over 99 times. And we wanted to find just what's the best magic number. What's the number of attempts that is best, that is helping us, but does not create too much noise. And by noise, I mean more messages. Any failure is another message, is another attempt to open a WebRTC connection, which means more signaling, more messages to the backend, and overall tons of messages that are sent. So the graph above is the number of attempts. The x-axis is just the max allowed attempts per user that we allowed. And the y-axis is the number of attempts overall. So you can see, obviously, the more attempts we allow, the more attempts overall the system has, and that costs money. That creates more traffic and bandwidth you need to deal with. And the graph below is the success ratios. We played with it. We wanted to see what number works the best. And we found that it was 4 retries. But there's one interesting interesting topic before we reach that. some small group of bad users somewhere around the internet create a lot of problems to the rest. And that's, again, very specific to us, to our use case, because, I mean, let's say you want to create a session, a voice session with Tzachi, and he's a bad peer, obviously, everybody knows that. He's not connected, so you're probably going to give him a call, or you're going to send him an email, hey, I'm trying to connect with you, but you're probably in some very restrictive network, and I cannot connect with you. And there's not a lot you can do about it, other than use turn or something like that. In our use case, one single bad user at Tzachi can just create tons of noise because hundreds of users throughout the life cycle of his session can be connected to him. So we want to detect that quickly and stop connecting with those users. So we came up, also there's a trade-off, obviously, and we came up with just limiting, once we find a peer that has more than 95% failure ratios, we just blacklist that user. So we'll not attempt to connect to other users, and no user will attempt to connect to that user. And that reduced the number of total messages by 50%. That's huge. The trade-off is that we lost 1.5% success connections. Because sometimes there are false positives. Maybe we thought it's Tzachi, but it's not. Sorry, Tzachi. So the conclusion here is that retrying definitely helps. Again, very specific to your use case, so I encourage you to think, what's happening in your app, and you can play with it. Eliminating the bad peers, detecting them and eliminating them definitely helps. It comes with some cost, but there's a trade-off, and for us it worked. And that's how we saved 50% of the matching messages on the server. It's still ongoing work for us. We found some interesting data recently. There's very big variance in different networks around the world. Some ISPs are more friendly, so peers that are coming from the ISPs have high likelihood to succeed in connecting with other users, while corporate network or some ISPs are very bad in that terms. And it's good to be aware of it and know that in advance when you build a mesh network and you want to connect different users. Another surprise for us was browsers, and we're still not sure if maybe it's correlated to some other data or it's actually the cause, or the browsers are actually the cause. So Firefox has a very good success ratios on average. Then come Chrome, Opera, and Safari. And we're still trying to figure out. If you're interested about it, please ping me, and we can keep in touch and let you know what we discover. I'll go over it real quick. The other stuff that we work on, just some bugs that and WebRTC developers know about, and we still worry about it, and we try to move it forward. Actually talked earlier with one of the Google engineers, and I think we're going to be okay. In general, Google has been amazing, and the WebRTC community has been amazing in building very good interoperability between browsers, and the state right now is that everything works much, much better than what it was when we started. That's it. I'll be happy to hear questions.
Okay. Yes?